Okay, hello. So my name is Rasmus Magnusson. I'm currently doing my the last few months of my postdoc, and I have mostly in my research career been looking at different kinds of ways to model biological systems, where the last 4 years, I would say, have mostly been revolving around deep learning and neural networks. So I'll just share my screen here for a presentation. Neural networks. I'll give this presentation where I think we will start by just getting a feel as to why neural networks are so great that they are as they are, as great as they are, and then we'll move on to the development of how we got where we are today in neural networks, and then exactly we will just scratch the surface a little bit on how they work under the hood, and then finish with looking at some examples of how they function and different kinds of neural networks. Okay, so neural networks, they and deep learning is what generally the media refers to as AI, somewhat sloppish maybe. They have really gotten popular the last years, and people have seen them been using them to generate images and interpret images a lot. That's basically have been their most prominent success case, I think, and also at interpreting images. And they're used today in self-driving cars and anywhere where you want to have a fast way of interpreting images. And generative AI has also gained a lot of prominence recently. ChatGPT, I don't think anyone missed that by now. This approach where you can generate very, very complex patterns using different kinds of neural networks. And perhaps most importantly, we also have AI and neural networks becoming very integral tool in bioinformatics and systems biology, such that we use them to understand biological systems within microbiology and all kinds of image analysis in medicine, of course, too. And I think we'll now have a look at exactly why that is. So, as I said, I have been working with systems biology and models in models of biological systems now for a few years. And when I started, I did mainly the kinds of mechanistic models that I know this course also touches a little bit on. And there you have you look at small systems, small biological systems that you embed very, very complicated math into, and you try to explain every single aspect of exactly what the system is doing, and you take biochemical reaction equations and you use the math that we know from there to get as close to a true mathematical representation of a biological system as possible. And while that is a very, very powerful way of modeling a biological system, the limitation is that the complexity and especially the non-linearities of such a system requires very complicated math, and by that you're also limited into not having models that stretch more than a handful of players, or a little bit more than that, depending on exactly how much you put into the system, how much effort you put into the modeling. On the other side of the spectrum is larger statistical models, where you move away from the mechanistic understanding of the system in order to explain a much larger biological system. And when you do that, you usually assume the system to be linear, or that is one of the more common ways of doing it, I would say. And you have very simple equations explaining data. And when you do that, you can fit a lot of things to your model, or you can fit your model to many different, depending on what you're modeling, genes or proteins or methylomics and basically any kind of data. But you will also have very unprecise models that since they're statistical assumptions based in statistics mostly, they will contain lots of false positives and false interactions that maybe are not there in reality. So the main question, as I see it, is can we go both big in terms of model size, but also have some kind of modeling technique that captures very complex system behavior? And it turns out that neural networks are ideal for this kind of application. And before we go into exactly why they are ideal, I think it would be great to look at the history and how neural networks have come to be the dominant form of modeling or machine learning, I would say, in terms of research outputs today. So the least functioning unit of a neural network is quite easy to understand. So I think we could start by looking at that, and then logical start would be the perceptron, which is the smallest part of a neural network, you could say. And they were actually developed, they have been around for quite a while. They were developed back in the 50s even, where Rosenblatt and al. Searched for a way to classify data. And there are many different approaches to have a model that classifies data to belong to group A or B. But the way they looked at it was using how neurons in the brain work. So let me just get a pen here. You have a neuron that is either activated or non-activated. In mathematical terms, it's either 1 or 0. One would classify input data into group A, 0 would classify data as belonging to category B, I would say, in this example here. And then you feed data from the inputs into this output neuron, depending on some kind of mathematical expression. And perhaps it becomes a little bit clearer if we work from an actual example, and I chose the Titanic disaster as the example, and that is actually one of the most common example data sets when it comes to working with machine learning. So don't be surprised if you see the Titanic disaster data sets popping up in future lectures, or if maybe you're already familiar with it if you've taken a few courses in machine learning. So here we want to predict if a passenger on the Titanic will survive the later catastrophe. And we will say that if the model outputs a 1, it's likely we predict that the person will survive, and if it outputs a 0, we predict a fatality. And here I've just chosen at random 2 predictors, 2 input variables. The first to be whether or not the passenger is in first class, because I know that a lot of people in first class had a much higher chance of surviving than not, and also age. And here I'm at least speculating that since women and children board the lifeboats first, that the younger the passenger was, the more likely it was to actually get a place in the lifeboats. And then you have between these input parameters x1 and x2, first class and age, we also have a parameter, one parameter for each respective input variable, beta 1 and beta 2. And beta 1 I chose here to be positive because I'm thinking, as I said, first class A1 would have a bigger chance on giving a survival here on the output level. And age, there's a negative one because it's a negative dependency on age for surviving the catastrophe. The model we choose here is just the sum of the coefficients and the predictors fed into an activation function G, because just as in a brain cell, we want the neuron here on the output level to only become activated when it reaches some kind of threshold. So here we see how an actual activation function G, a sigmoid function. You can choose when you design your neural networks to have basically any kind of activation function. But if you're trying to classify data, the sigmoid is one of the most common ones. And here you will see that if it crosses the inputs to G here, crosses 0, you pass above a prediction value of 0.5. So that would mean that we are actually predicting the person to be a little bit more likely to survive or not. Okay, so that is the most simple part of a neural network that you could think about, that you could think from. That was back in the 50s, and a little bit later on in the late 60s, people started experimenting with stacking these perceptrons into bigger, more complex models. And what they saw was that since you have for each activation function, for each node in this stacked set of perceptrons, you introduce one nonlinearity. And if you have many layers of hidden variables here in the middle of what is now a neural network, it's a network of many perceptrons. Since you introduce nonlinearities, you actually, the bigger you get, the more complex dynamic you're able to model between the inputs and the outputs. So you're making the model more powerful in terms of what kind of dependencies it's able to implement. But that kind of modeling technique didn't really take off much in the 60s. It would actually take until the early 2010s, when an algorithm called backpropagation was invented. And why would it take such a long time? Yeah, because as you saw earlier, you have one parameter. Basically, if we reach the line here, you have between the neurons, or between the hidden variables, as they're also called, hidden nodes, sorry. And as you understand, you quite quickly get a lot of different parameters. And if you have a lot of parameters that you want to train in order to get a model that actually explains data, that means that they're getting more and more complex to find the correct values for. But backpropagation solves that, and it does that by calculating the gradients of how the model fits the data, and updating the parameters step by step, starting from the back, that is the latest, the last output layer here, and then going iteratively back towards the input layer, and that is why it's called backpropagation. So when training this, you have your input data x and you have your response variable y. You feed your input data into the model. You get a prediction y hat. You take your the actual true data y. You feed it into a loss function. So loss function is what you call the function. Well, in machine learning, in deep learning, you call the equation that calculates how well the model fits data the loss function. I think you can also hear cost function or objective function within other kinds of modeling or optimization problems. Anyway, the loss function calculates how well y hat and y how much similar they are, perhaps by mean squared error or there's many different options on how to actually calculate that. But you get a number, and you can use that number to update the weights. Basically, you choose the new weights, beta n+1, to be equal to the old weights and minus some kind of step in the along the gradient. So what you're doing is you're basically just walking down the hill in the cost landscape. That is the loss function. So you're finding where the discrepancy between y hat and y is the smallest. And that actually works surprisingly well when it comes to neural networks. Okay, so that was a very short introduction on how neural networks function in reality. And that could be that was a general presentation that is true for any application in machine learning. So the question now is exactly why is this important when it comes to bioinformatics and systems biology and trying to use this to explain biological systems? Well, as you saw in the earlier slide, as I said, you have a lot of parameters, so you also need a lot of data to train these networks. Actually, a lot of data, and it's only until very recently that we have been able to extract lots of data from biological system. If you look at the cost per sequenced genome, for example, the price has really collapsed. This is a logarithmic scale, so you see that it's today much cheaper to do many different kinds of biological experiments, and by that we also have a huge set of available biological data, depending on, well, I mostly work with transcriptomics data, and these are all databases that have transcriptomics data for lots of different patients and lots of different tissues. So it's very timely, and we have right now, I think, a great opportunity to use neural networks on the vast amount of data that are available to us today. And then neural networks also, of course, come very handy in the development we've seen the last 10 years there too. Okay, so I thought that in order for you to just see neural networks in action, we could have a look at some very basic example of neural networks. I think it all becomes a little bit less abstract then if you just look at exactly some kind of example. So here, this is Google's implementation of a neural network in their flagship, the programming language TensorFlow, which is a Python implementation of doing neural networks. So here we're having data. We can choose what kind of example you're looking at. So here we have you want to classify between these orange and these blue dots, and it's now we choose some data to come from a checkerboard kind of installation. So it's a non-linear dependency on x and y. in the input parameters. You can design your network of what you want to input, the x and y coordinates, and you can have number of neurons, number of hidden layers and number of hidden neurons in each hidden layer of this neural network. And then you have this output here. You have the activation function that was sigmoid, now it's tan-h, which is a trigonometric function, and also how fast you want to move along the gradient, which is also a great way to show that if you play around with this page, and I really recommend you guys to visit this page later on and play a little bit with neural networks to just get a feel of exactly how they function. So the learning rate is how fast you move along the gradient, and if you move too fast, you might jump over important slopes and end up in completely wrong places, so in the loss landscape, so you don't really fit the data anymore. So do not take this too big. So here we see now I started, which means that the model is updating the weights of the parameter, that is the parameters iteratively here. And you can see that now the model actually fits the data quite well. So that, and you can also look at what each hidden neuron in the model here represents. So you can see some kind of representation of data here, exactly what each neuron has learned, and how you go from linear things until to becoming more and more nonlinear as we go along. And maybe this model actually has too many layers here, because yeah, already here I think I have a very good representation of the data. Okay, just speed up around. So this is an introductory course on neural networks, and I think if you're interested in learning more, there is this YouTuber called 3Blue1Brown, which is really good at explaining both the general concept of neural networks and also go a little bit more into the savvy details of how the backpop works. You can learn a little. You can really learn a lot on what they do. You're interested. So, and also since I know a lot of you guys are starting to become engineers, and this YouTuber is also great for a lot of other explaining a lot of other methods that you will encounter in many different courses and maybe in your future careers as well. Okay, we're getting closer to the end of this presentation, and I thought maybe we could finish by looking at different configurations of neural networks, so you at least heard about them before we end the session. So everything I've been showing you so far are examples of feed-forward neural networks, which basically is the vanilla configuration of a neural network, where you have a flow. Where is the here? Where you have a flow from input to output. It's linear. Each layer here passes on the values to all nodes in the next layer. It's basically very easy to understand. But the main success case, and it might be good for you to know that, in terms of deep learning, has been the convolution neural network, which is mostly applied to images. And when you have some kind of important structure, such as an image could be viewed as a matrix of values, that is pixels, and they just don't occur on random, but this pixel being close to this pixel actually means something, and they're connected. So in convolutional neural networks, they use convolution, which is a tool applied in image processing. And I think if you've ever taken a course in image processing, you would have used convolution. In Swedish, it's named falkning, if you are familiar with the English term. Which is basically that you have a filter that you slide over this matrix and then calculate a value by multiplying the filter with the pixel values. giving one output value for each position that you can have this filter in the matrix. And you do that for all possible positions in the on the inputs. So you get a matrix representation here, and then you can continue adding convolutional layers and also feed-forward layers that we saw before. So you have a model that can find patterns wherever they appear in the image. So if you have a hat up here, you could recognize that, but also if it's down here, and you wouldn't be able to do that if you have the rigid structure of just a feed-forward neural network. And I also briefly mentioned autoencoders, which is a special case of neural networks. Here I've drawn it as a feed-forward, but it could also be a convolutional neural networks. And autoencoders are the special case where you have input data X that you feed into a model, but you're also trying to predict the same thing, X here. So you're compressing X into a set of fewer variables and then decompressing it back into the original inputs. X hat here. And the reason why you do that is because if you remove, or if you go from having a many dimensions of your input data into fewer, you lose lots of noise because the model can't afford to model the noise, or it cannot model the noise. So you actually denoise data by doing that. And there's lots of other interesting features of the autoencoders as well. There's also tons of different generative configurations of neural networks, but I think if you're interested in those, you can also look at YouTube, for instance, cycle GANs or GANs in general are very interesting applications of neural networks. And I really recommend you, if you're interested, to have a look at that. So the take-homes of this introduction are basically that neural networks are very powerful models that can learn nonlinear dependencies between inputs and outputs if they're big enough. But when they get big, and they do get big, usually when you try to do something, they also require a lot of data to learn properly. That is the main drawback, but we're getting big data right now. So in most fields of biology, you're getting lots of MRI scans are building up. The amount of available MRI scans are building up. And also, if you look at different omics techniques such as transcriptomics, metabolomics, all those kinds of things, we're getting big data sets all of a sudden. So I think it's the outlook for neural networks in bioinformatics and systems biology and for the use of digital twins is looking great. And that was all I had to say for today. Thank you for tuning in, and I want to say good luck with the rest of the course.